Welcome everyone. Thanks very much for joining. We'll be talking about building optimization models from pandas data frames, and specifically about a new open source package that we've been putting together to help make it a little easier, a little more efficient to build Gurobi models when your input data and your output data need to be within the pandas ecosystem. Maybe just additional housekeeping note. So I'm presenting this just as a Jupyter notebook. It's using the Rise plugin to turn this into slides. And if you'll see in the chat, I think Gwyneth has posted the link a couple of times now. So the slides are actually available in the GitHub repository for this project. So if you want to grab that notebook and follow along, or just have a look through the repository afterwards, you'll find all the material there. So with that, I'll get started. Okay, so maybe first of all to explain a few of the words in the title, just to make sure everyone's familiar with what we're talking about. Hopefully if you joined, you're familiar with at least one of gurobipy or pandas, but I'll just give a quick intro to each one first. So gurobipy is the Python API for the Gurobi optimizer. So the optimizer is the core solver engine that Gurobi develops. It solves mixed integer nonlinear or mixed integer quadratic programs, and everything falls underneath that umbrella. And gurobipy is the Python API for building models and then solving them, extracting solutions. This is commercially licensed software. It's developed and supported by Gurobi. If you're an academic, you can get free licenses for research. And if you're a commercial customer of ours, or a new commercial customer of ours, you can also reach out for trial licenses. The documentation for gurobipy all lives on the Gurobi website. And the aim of the package is to provide a sort of one-to-one translation layer from a mathematical model to Python code. So I've put one of our sort of simplest examples on the slide here. So if I'm just trying to maximize a simple function of 3 variables under a couple of linear constraints, then I create each of these variables as Python objects using the add_var function of gurobipy, and I can set the objective by just writing out in code using those objects, the objective, the constraints, and this all uses standard Python operators. So the aim of this package is to just make that translation really, really easy if you're working in Python. As for pandas, so pandas has really become I guess a standard tool for data analysis, data manipulation within Python. It's part of the whole PyData stack that includes a whole lot of other packages for machine learning, for data visualization, and so on. This is an open source package. It lives on GitHub, and it's run by, it's handled using the usual open source process. So a handful of open source developers and taking contributions from the community, but it's sponsored by NumFocus, which has helped really drive the project along. Their documentation lives under the PyData website, and the main thing this package provides is DataFrames implementation for Python. DataFrames came out of, I think, the R community initially. Probably they have a longer history than that, but Pandas provides this implementation to store data in a column-wise format and provide vectorized operations for manipulating it. Provides a lot of I/O features for reading from many different data formats or web endpoints, database connections, and tools for analyzing and plotting that data are built into the package. And this has really become the standard package for analytics projects in Python. And what's quite interesting about it is that if you're working in an analytics project and you want to take your initial data analysis and move to a sort of prescriptive analytics step that often involves building an optimization model, you have to take that pandas data input and somehow feed it into an optimization model. And this, at the moment, has provided a few challenges working with gurobipy, which is what we're working to resolve here. So that brings us to gurobipy-pandas. So this is designed as a linking package between the formulation package, the model formulation package, gurobipy, and the data manipulation and handling package, pandas. This is an open source library as well, so it's living on GitHub. It's published on PyPI, so easy to access and use. The package was developed by a few, I guess, pandas enthusiasts here at Gurobi. And we had some really valuable input from Princeton consultants in particular. So I did want to thank Irv Lustig and Robert Randall for their input and their advice as we've been developing this. The documentation for the project is hosted on Read the Docs. So this is public, easy to find, with it sort of built in the normal Python style for documentation. And the aim of the package is to allow users to build Gurobi models a bit more directly from pandas data, and in the same vein as gurobipy, that you should be able to translate a mathematical model kind of line by line to very readable code that suits both a pandas user and someone who's familiar with optimization. So over the course of this session, I'll give a bit of an overview of the design of the gurobipy-pandas package. So what principles we've followed and what we're aiming to do. I'll walk through some basic examples of the usage of the package. So how to create variables, how to build expressions that combine the variables you've added to a model and the data that's coming in from the data incorporated into the model, how to create constraints, and then how to retrieve solutions in a pandas format. And I'll go through a complete modeling example and just close with a few points on usage of the package. So on to design principles. So what we're seeing is there's a nice correspondence between how a mathematical model is built and how pandas deals with its data structures. That gives us kind of some clear anchors for writing code that incorporates both packages. So maybe to get some terminology down first. So if we have a very simple mathematical optimization model, so this is just a single knapsack model in this case. So we're maximizing over a linear objective. We have a single linear constraint, and we're optimizing over a series of binary variables. This optimization model, one of the main basic elements here is the index. So there's an index set I, which defines both our series of variables and both of our sets of data. So there are values for each item in the knapsack, which are defined over this set I. So I have a series of items, and each one will have a value. Each one will also have a weight, that's A. And we need to associate with each of those items a binary variable also indexed over that same set. So one variable per item. So the entire mathematical model is built over this index set, and all data, all variables, and all constraints are defined over those indexes. And this gives us quite a clear way to structure data in code, which I'll show in just a sec. The reason I emphasize that data indexes variables idea is that pandas data frames and series are structured in the same way. So a data frame has an index. So I've just generated a simple random data frame with an index, a couple of columns, and some numeric data. That data frame has an index which is the row-wise index for this data frame. And it has a series of columns. So each of these columns are sets of data over that index. So if we think back to that mathematical model, we could think of each entry in this data frame as a numeric entry, AI and BI, so A0, A1, A2, A3. What we're sort of missing if we want to cleanly build mathematical models from this is a way to define variables over those same indexes and to build constraints over those indexes. And that's the gap we're trying to fill. So that leads us to, I guess, what we've aimed to provide within this gurobipy-pandas package, which is some specific methods to create pandas indexed series of variables. So this gives us the tools to incorporate, to construct a pandas series containing Gurobi variables or representing Gurobi variables. We'll need some methods to build constraints from mathematical expressions. So that knapsack model I showed had just a single constraint, but more commonly there will be an index over which all constraints are defined. So we'll need a way to build that set of constraints from a series of expressions. And we'll also need a way to read out solution values. So in gurobipy, this is done via Python objects, but we want to kind of lift that up to return solutions directly as pandas structures. So these are the three main features that gurobipy-pandas is adding to the existing gurobipy and pandas code. We're fortunate a bit in the way pandas is designed in that we can actually leverage the existing logic in that package to help us build quite complex mathematical expressions. So pandas already has notions of algebraic operations and so this split, apply, combine logic that's used for group by statements in particular. And this all uses very well-known syntax and methods if you're an existing pandas user. So I'm going to show a series of examples throughout this talk to show how we can use existing pandas operations to build mathematical expressions. Okay, onto the real code. So initial setup for building a model in gurobipy-pandas is pretty straightforward. So as I mentioned early on, the package lives on PyPI, so we can just go ahead and pip install it as you would any other Python package. The only dependencies of the package are gurobipy and pandas, so the appropriate versions of those will be installed by pip as well when we do this. And then the most programs that you write using gurobipy-pandas are going to be preceded by these imports. So you'll be importing pandas at some stage where we need to use pandas methods directly. We'll need gurobipy. So gurobipy-pandas is not so much a wrapper package that replaces gurobipy for building models. It's really a linking package for specific components of model building. So you do need to call gurobipy methods directly in a lot of cases. I usually have a GRB import in my code. So this refers to various bits of variable typing information or options needed to configure the solver. And then we import the gurobipy-pandas package itself. This import does a couple of things. So I'll show over the course of the examples, but it imports a couple of methods under this GPPD namespace, but it also adds a pandas accessor to DataFrames and Series, which hooks into pandas' existing methods to provide some of the functionality we need. Two more inputs that I've used two more setup statements that I've used in this code that we would not recommend you use in a production environment, but is quite handy when you're doing a demo. There's an interactive mode added to gurobipy-pandas. This is so if you're familiar with gurobipy, you'll know that if you add variables and constraints to a model, It's not possible to read that data back immediately until you've performed an update on the model. What we did with this set interactive mode is just for any gurobipy-pandas method that you call to add variables and constraints, it will perform an immediate model update. It's just a simple trick within this notebook to make it easier to just immediately see changes to a model. But it would slow things down if you use this under normal usage. So it's really a debugging trick only. I've also switched off all the logging output for Gurobi, which again, in general, you don't want to do. But in this presentation and throughout this notebook, I'm really focusing on the inputs and outputs to a model rather than what the solver is doing. Okay, so overall, given those imports are done, I'll just want to briefly sketch which package is used where. So gurobipy is still sort of the entry point for building models this way. So when you create models or when you kick off an optimization run within your modeling code, this all uses the standard gurobipy methods that you're used to, which means any constant status codes, error messages that you need to check, they're all being emitted from gurobipy. Gurobipy-pandas just provides a modeling layer on top of this, which provides both pandas accesses and free functions that create sets of variables, create sets of constraints, and extract solutions. So whenever I'm starting a new model, I'll need to create a gurobipy model, first of all, as my entry point. And this leads us to our first actual use of gurobipy-pandas. So there are a couple of ways of doing this, but the simplest option and the first way I'll present is that there is, having imported gurobipy-pandas, there is a free function called addvars. And what this function does is I can pass any pandas object to this function, and it will create one variable in a gurobipy model for every entry in the index of that object. So I can pass it an index to create a variable per entry in that index, or I can pass it a series or a data frame to use the index of that series or data frame for the same purpose. What it will return is a series of gurobipy variable objects, which are over the same index and which have names constructed based on the index values. So just to give a very brief demonstration of this, I've created a simple index object here. This is just a pandas range index representing values 0 through 4. It doesn't matter what kind of index you use. So you can use a string labeled index, you could use a time series index, you could use an index that doesn't start at 0 or a non-continuous index. Gurobipy-pandas will handle all of these cases. And all I need to do to create my set of variables is pass to this addvars function the model, my index object, and a few options. So I can pass a name here, and what I'll get back is a pandas series indexed over the index that I passed in, with a variable for each entry in that index. So this is a variable that's been added to the gurobipy model. And those variables are named based on the base name string that I pass, and the entries in the index. So it's very similar to the addvars function in gurobipy, which would construct a similarly structured dictionary with that same kind of naming feature, that same automatic naming feature. I can also set attributes at this stage, so I can say I want all the variables in this series to be binary, like I would in that original knapsack example. And this is done the same way you would with existing functions in gurobipy. I pass the vtype argument here, and this will be a series of binary variables that I've returned. There is a second option for creating variables, and which one is appropriate depends a little on the style of model that you're building. You'll find examples of both cases in the documentation. So the second option here is to use the data frame accessor that we've added as part of the package. So rather than calling a function to return a series of variables, this approach hooks an accessor onto a data frame and will return a new data frame with an appended column of variables. So I've got a very simple data frame here with just a single data column U and over index values 0, 1, and 2. To call this accessor is a method on any pandas data frame. So just importing the gurobipy-pandas package is enough to register this accessor. And by calling this, I pass this a model. Again, I pass it a base name string, and I get back a new data frame with an appended column of variables. So one variable, again, has been added per entry in the index. Those variables are named based on that index. And I get back a copy of the data frame. What I can also do is say that I would like to take the upper bound values of the variables based on an existing column in the data frame. So this will set the upper bound of y0 to 1.4, the upper bound of y1 to 0.2, and the upper bound of y2 to 0.7. I can do this for any attributes that I need to populate. The reason we've got this method as well as the free function is that this allows you to do some nice method chaining tricks. So this is a fairly common style in Pandas to take a data frame through a series of transforms by building on by calling methods on that data frame, returning a new data frame with some appended or transformed data, which you can then continue to work with. So I could continue adding columns of variables. I could build quite simple constraints this way. Okay, so next step after adding variables is to look at creating some mathematical expressions. So we're not really adding anything here with gurobipy-pandas. So what gurobipy-pandas is trying to do is get you the right setup. So build your variables natively as pandas series, and then we can directly we can leverage Pandas's own functions to build our mathematical expressions in order to formulate constraints. So the common operations that are going to come up here is summation. So we're likely to need to sum over a series of objects. We'll need to construct some simple arithmetic operations like addition of two series or multiplication by scalar values. And we'll need group by values to build large sets of constraints in a simple way. So let's have a look at a few basic examples. So just some setup to show what I'm doing here. Let's think about a mathematical model that's constructed over a single index I. So my index I in the mathematical model is going to be represented by a pandas range index. I'll have some variables, xi, and that's going to be represented by a series of variable objects, which I've constructed using gurobipy-pandas. So this is the index is I in my code. The variables are a series called x. And I'll also have some data. So just I have a numeric series C to represent also over the index I, which represents my data entries ci. And then given that I've got my initial data built this way, I can apply basically any pandas operation. So a first port of call might be to construct a set of simple linear expressions. So if I want to construct a series of mathematical expressions, which are each 2xi plus 5, so I need 2x0 plus 5, I separately need 2x1 plus 5, and so on. So I'm creating one of these for each entry in the index. Given that I already have x as a pandas series of variables, I can just write directly 2x plus 5, and I will get back a pandas series which contains, over the same index, a series of linear expressions. All right, so I've got each of these expressions entered here. And there's no magic we're adding here. This is just what pandas will do for you natively. So slightly more interesting step, if I want to construct a single linear expression, which is a sum over a given index of every variable in that index, then Pandas provides something for us here as well. So I had my series X of variables. I call the Pandas function x.sum on that object, and what I get back is a single Gurobi linear expression, which represents exactly what I've got mathematically here. So this is going to sum over the entire index, and it does exactly what Pandas would do if you had a data series. You get back, if this was a numeric series, you'd get back a single value. This is a series of variables, so you get back a single linear expression. I can also perform some arithmetic with series. So if I need to build, given my numeric series C and my variable series X, if I want to construct the linear terms Ci, Xi for each I in my index, then I can do this using just an element-wise product. All right, so I take my two series C and X, I multiply them together, and Pandas will give me back 1 times x0, 2 times x1, 3 times x2. So directly aligning the series C with the series X and carrying out each of those products. So I have here a series over the index I, which represents that set of terms, Ci, Xi. And then I may want to sum up those results. So to get a single expression which sums over the index I and takes that collection of terms Ci, Xi, I can take the C times X series that I just computed, call sum. Again, that's the Pandas inbuilt sum, and get back a single linear expression. So here I've got my linear expression representing my mathematical object there. Okay, so hopefully that's looking very familiar. Those few slides, if you're a Pandas user, should behave exactly as you expect. If I'd replaced X with a numeric series there, you'd get exactly the same result, but computed on the numeric data present there. So this gives us a very familiar way to build mathematical expressions, and any operation you could do with data in Pandas, you can do the same way with these data and variable series there. If you're familiar with the data types in Pandas, it actually is at the moment just a series of Python objects that represent the variables. So we can manipulate it in just the same way. But there's a much more interesting level here, I guess. So far, we've only seen things over a single index, which builds very, very simple models. What we need for more complex models is to build variables and deal with data over multiple indexes. So Pandas has a concept of a multi-index here that will help us. If in a mathematical model I had some piece of data which was Pij, then the way you would represent this in Pandas is we'd use a data frame or series. In this case, I've got a data frame with a single column representing the values of P and a multi-index. So Pandas has here an index with two levels. The first level is I, the second level is J. And in that index, I have various combinations of I and J. It's actually sparse, this index, so I don't have, you can see I've got values 0, 1, and 2 for I, and also values 0, 1, and 2 for J. But what I don't have is every single combination of those values. So you can actually construct your data in a way that suits the model, in that only allowable combinations over which this data entry P is defined will be captured in the data frame. So what we're going to need then is a corresponding set of variables. So if we have multiple indexes in a mathematical model, then we need the definition of a variable, say Yij. And this is straightforward to build now that we've got gurobipy-pandas, because I already have a data frame data, sort of unimaginatively named. That data frame has this multi-level index. And if I pass this directly to my gurobipy-pandas add vars function, then I will again create one variable per entry in the index. That variable will be given the base name that I pass in as the name argument, and the rest of its name will be constructed based on the multi-level index values. Again, kind of similar concept to what you'd see with addvars in gurobipy. What I get back is a pandas series across the same multi-level index, which maps those index values to each of my variables. And this allows me to do some much more powerful things when constructing models. So I have my variable yij defined over two indexes, and a common mathematical expression to put together would be to partition over one of those indexes and somehow aggregate over the other index. So a first step would be, let's say for each value in my index j, I want to partition, I want to collect all the y variables for that index j, and I want to sum over the I values corresponding that correspond to those entries. Or I want to sum over all the valid I values associated with that index j. And what I should get back is a single linear expression for each index entry j. And pandas gives us a native way to do this. I can group by the index j and then sum over the remaining indexes. So when you're building expressions like this, you'll see that your kind of for all part of the model should line up directly with what you pass to the group by. So this is the partitioning index. You then call the pandas sum function as you would with any other grouped aggregator that you use with pandas. And it will sum over, in this case, it implicitly sums over the index I because that's the only level left. Right, so pandas understands you want to sum over everything you haven't grouped by. And then what I get back is a pandas series representation of exactly that mathematical model up here, mathematical expression up here. So at index value j equals 0, I have y1, 0 plus y2, 0. At index value j equals 1, I have y0, 1 plus y2, 1. So this is collecting each of the y terms with the given index j and collecting the results. I'll also need commonly some way to align data over these multi-indexes. And so for example, I may need to build a product cj times yij for every value ij in my index. So mathematically, what I want here is to associate a piece of data over index j with a variable yij, and these should line up based on the same index value j. So for each yij and cj, I'm joining them on the corresponding j. And pandas defines how this alignment is done. So it's a join operation, and it does pay attention to the names of your indexes to do that join. So if I had built let's say I built a series C, which is just over a single index, so only over an index j, this represents my mathematical terms cj. I already have my variables y over the multi-level index. By just doing a straight multiplication between these two, pandas understands to align these based on indexes with the same name. So what I'll get back is a series of expressions indexed over the pairs ij, those same pairs that I had for the variable y, where each term is an entry from C for the corresponding j multiplied by that y term. So I've built a series of linear expressions representing, again, exactly that mathematical object. So the important thing to understand here, and I briefly pointed this out, is that these are the alignment here between two series is standard pandas logic, so that all this alignment, all the arithmetic is performed by pandas, and it behaves exactly the same way as it would for numeric series. Pandas has a handful of well-defined concepts here. So there's joining, matching, aligning, broadcasting between series, between data frames. And because we're using a native pandas object to store all these variables, you'll get the results you expect. And finally, I think we finally reached an interesting example here that will build a more complex object. So if I take this series I previously constructed, Cj times Yij, a natural thing to do would be to then partition this over the index I and sum over all my j indexes. And this is applying the same group by and aggregate operation as I did in the single in the case where I only had Yij here. I should get back a series indexed by I, where each entry in the series represents this mathematical expression. And this is, I'm really just appending that group by operation on the end of the C times Y product that I computed. So I group by I, that's corresponding to my for all partitioning index here. I sum over the remainder, and what I get back is a series index by I with each of these aligned terms aggregated together. Okay, so with adding variables and building basic mathematical expressions under our belt, the next piece of the puzzle that gurobipy-pandas is adding is a way to build a set of constraints from those mathematical objects. So I'll continue building on the example I had, which is I'm grouping over index I and constructing a series of linear constraints where the left-hand side is my sum over index j of Cj times Yij, and the right-hand side is some numeric values Bi. So on the previous slide, I already constructed this series, C times Y, group that by I and sum the result. I get something which is indexed over all my index values of I. And then I'll add some data into the mix here. So another numeric series B, which is indexed over exactly the same I values and has numeric type. So I've got the left-hand side and the right-hand side formulated as a pandas series. And then the method we're using in gurobipy-pandas here is this free function add constraints. We pass this the model, a series representing the left-hand side, the inequality or equality that we need to use. So that's usually referred to as the sense in Gurobi. So less than or equal to, or greater than or equal to. And we pass it the right-hand side series, and we can name the constraints as well. And what this function will do is it will align these two series the same way that pandas would, and it will return a new series indexed over the same common index that these two series share. And it returns a series of constraint handles. So these are gurobipy constraint objects that give us a reference to the constraint. I can do a simple check here just to make sure this built the constraints I expect. So there is a function within gurobipy called getRow, which extracts rows from constraints. So you're effectively extracting all the linear terms involved in a constraint. So if I just use Pandas's element-wise apply operator with that function, I can read back the coefficients that were added into the model. So these are handles to the constraints that I can read back data with. I can also check the right-hand side values came through as I expected. I'll go into this syntax a little bit later. This is another accessor that we hooked onto Pandas series to help read back model data. Its main use is to read back solutions, but we can read back really any attribute of variables or constraints. I do want to make one very important point here about missing data. So in the previous example, I built my series B on exactly the same index values as the grouped grouped arithmetic expressions that I'd previously built. So I had one numeric value associated with every expression and aligned on an index I. Let's instead imagine a case where I'd built mismatched indexes. So I've built a series B, which actually has a longer range index. So there's one extra value here. If I took this new series and say subtracted away the series of linear expressions that I'd previously built, what would happen in normal pandas operations is I'd get a missing value here. And pandas handles this fine, but we would consider this to be essentially a bug in the data construction for the model. So if you try to build constraints this way, assuming it lets me move forward, there we go. If we try and build constraints this way, you'll just get back an error from gurobipy-pandas. So this is really indicating that something went a bit wrong in your model construction, and you should go back and review which indexes are correct. So the library is quite strict in that sense. I mentioned a secondary way of adding variables before via accessors. We have that same approach for constraints. So there's an accessor hooked onto pandas data frames, where if I have an initial data frame using with a numeric series of values p, I can call add vars in this method chaining style to start adding single columns of variables to new data frames. And then I can continue that method chaining approach with an equivalent add constraints accessor. So this will add one constraint per row based on the entries available in that row, both variables and data. And there's a pandas eval-like syntax that you can use here if you're familiar with that. So we'll create a set of constraints in a vectorized way that each represent y plus z less than or equal to 1. So for each entry, I create a separate constraint. Okay, and then the last piece of the puzzle in model construction. There's no actual gurobipy-pandas method for this because there's no need to vectorize this over an index. When I'm setting an objective in a model, I can just take any linear expression resulting from my pandas data and pandas series. So I have my series variable y. I call sum on that method to get a sum over all those entries, and I get back a Gurobi linear expression object. And I can just pass this to set objective as I normally would. So with the model construction done, what we need is a way to solve these models and read back solutions. So if you were working gurobipy, you'll be familiar with the x attribute of variables. So this is where we retrieve solution values from a single variable object. What we've implemented in gurobipy-pandas is a series accessor that vectorizes this operation. So this works for any attributes. I briefly showed extracting a constraint right-hand side before. And what we get back is a series of numeric data on the same index as the variable. So assuming I've already solved my model using model.optimize, I take my variable series y and I call this accessor gppd and then ask for the x attribute. What I get back is the solutions to my model over the same index as the variables y, with each of the final values, the solution values in the model as the numeric data in that series. Okay, so I spent quite a lot of time sort of building up the building blocks here. So I'm going to go quite quickly through a full example. You'll see it's actually shorter than it looks now that we've got those building blocks together. This is an abridged version of this project team allocation example that we have in the documentation. There's quite a lot more detail there, particularly around the sort of context of the model and where the data comes from. And I'm just going to briefly step through the constraints that we build here during the presentation. So brief overview of the model. I have a set of projects. That'll be my index, is an indexed over I, and a set of teams J. Project I requires a set amount of resources to complete. So this is a value WI, and each team has a given capacity defined by CJ. We get a profit value for a completed project, and that's dependent on which team completes that project. So there's data in this model, PIJ, and we're aiming to maximize the value of completed projects respecting team capacities. It's really under the hood a multiple knapsack problem. The key point to emphasize is that your data needs to be properly prepared before building a model like this, and this needs to be done before taking any modeling steps. So I've spent quite a lot of time focusing on using pandas indexes here and how to define data over those indexes. So the important point is that your model indexes should be clearly defined, and all your data frames, your input series, should be aligned onto those indexes. Our sort of golden rule here is any data reading and cleaning should be done before you start building models, and you should have constructed your data sets in the appropriate format before touching any modeling objects. So here the construction is fairly simple. I have a series of projects and a series of teams. Projects have a resource requirement. So I have a data frame here containing a resource column aligned to each of these project values in the index. I have capacity values for each team. So this is another data frame with teams as the index and capacity values as one of the columns. And I have my profit values. So this is over a multi-index because Pij, my profit values, are defined for each project and team. So what I have here is a data frame over a multi-index with containing my profit values. Interesting thing to note here. So for part of the definition of the model, and I really encourage you to go back through and read through the full example to make a bit more sense of this, is that not all teams can complete all projects. So maybe there's sort of another requirement that's not built in numerically, maybe a skill level that we know upfront which teams can complete which projects. What that means is that my data set for profit values is, it's not incomplete, but it's sparse. So part of the structure of my model is to say if there's not an entry in this project team data frame corresponding to a given index pair, then that team is not allowed to complete that project. So I have here a model over, there's 30 different projects to complete and 5 teams. So there would be up to 150 choices that I need to make here. But in practice, I have only 80 of those choices available based on other restrictions constructed before we even start building the model. So the structure of this data matches the sparsity of the model. And what's nice about structuring the data this way is when I go to add variables, I will get exactly one decision variable per entry in this data frame, which means I don't construct unnecessary variables. And that's one of the really common oversights we see sometimes in building models, is that too many variables are constructed and you need to go back later and add lots of constraints to eliminate those variables that you don't need. Far better to only construct the variables you need and rely on these grouping operations within pandas to still correctly build the right constraints. So what I've got here as a starting point is really clean data. My indexes I and J are correctly represented. The pairing, the multi-index IJ is also represented. There's no missing values and everything is correctly aligned. So every project appearing in this pairwise index has an entry in the project's data frame. Every team appearing in that pairwise index has an entry in the team's data frame. And then I'll step through this quite quickly because I think we've been through the mathematics in some detail now. As I said, I need to build my binary variables xij in this model, and I want only binary variables that I need. So I have my project values data frame. I will pass this directly to add variables, and I'll get back a new series of variables, X, which only contains the index values that I need. And I can actually build the objective very simply here, because I can assign linear objective values straight out of this input data frame. So here I'm just saying for each of the variables, I want each contribution to the objective to come from the profit column in the data frame. So this line of code builds all my variables and my objective in one step. I can build my capacity constraints. So we've seen basically this expression a few times now. I want to align my resource values requirements for each project with my multi-indexed series variable X, group that by my teams. So I'm building one constraint per team to represent that capacity. And then I need to align that with my team capacities, and that's done using add constraints. So I get back handles to those constraints. I've added in a simple vectorized way a series of constraints for each team to the model. I also need a constraint over projects. So this is an even simpler grouping operation. I'm grouping over each project I and making sure it's only allocated once. So I build each of these expressions by summing over the team's indexes of each project to enforce this constraint. And then lastly, that's all my constraints added. So there's pretty much, you can see there's a one-to-one mapping between a line in the mathematical optimization model and a line in the gurobipy-pandas code. And I can read back my solutions directly as a series. So I use the series accessor again to get back solutions. I get back a series indexed over my IJ pairs with binary values 0 and 1, defining whether a team was assigned a particular project. Because this is in Pandas, I can do whatever Pandas transformations I want at this stage. So maybe more commonly, you would be using Pandas read-write functions to write this off to another endpoint, or whatever the next stage in your analysis of the model is. What I've done here is just a few little tricks to pull together a data frame listing my project assignments for each team. And everything from this point onwards, after extracting the solutions, this is all just normal Pandas operations on a series. Okay, so that's about all I want to go through as far as examples. Just a few brief comments to finish up. So gurobipy-pandas is meant as a modeling wrapper to make it more convenient to read Pandas data in and out of a gurobipy model. It's best used where your inputs and outputs for your model are already naturally working within Pandas data frames, and it's critical that your data is structured in the right way to do this. So I'd recommend consulting the examples to make sure you're using the appropriate style. This isn't currently built to sort of make model building faster than you would be able to build in Python, but our main aim with this initial version is make sure you avoid performance pitfalls. So if you've used the variable construction methods we've got, the vectorized constraint operations that we've got in the package, and you follow this style of using Pandas group by operations in particular to build quite complex constraints, then you'll avoid some of the pitfalls we see when in some models integrating Gurobi and Pandas, which involves a lot of manual looping, repeated filters over the data, and so on. So the main point here is we wouldn't recommend taking an existing model, migrating it to Gurobi-Pandas and expecting a speed up. But if your data naturally lives in Pandas, then you should avoid some of the sort of major performance mistakes we see by using the package. And there's a dedicated page on performance with a few more tips on this aspect. One to pay particular attention to is the point I made about leveraging sparse indexes and making sure you don't create a larger model than you need to. So final thoughts, there are a handful of examples and we're still building on them in our Read the Docs page. So strongly encourage you to read through those to get a handle on the style for building various constraints. We'd welcome contributions to those. So where the project lives on GitHub, if you'd like to see an example added or you have an example you'd like to add, feel free to open an issue or a pull request. Same goes for reporting bugs or feature requests for that package. Feel free to do that using the GitHub repository. We've also got, so if you have usage questions on usage or want to just have discussions to have on the package, we use the Gurobi community forum for this. So there's a link to that in the README of the GitHub package as well, where you can post questions if you're curious about usage. And that's it. So I've run a little bit longer than I planned, but thanks very much for joining.